Okay, so gentlemen, today I'm going to go over the gas laws really quickly. I'm not going to go into too much detail. Uh, I will on Thursday do an online video where I kind of go through some of the problems on your worksheet and work through them. But I really want you guys to kind of figure out how to use these equations yourself. They're not that hard. The equations aren't super complicated. It's really just rearranging equations and plugging in numbers and solving for the correct variable. I will put a key up for the worksheet also probably on Thursday after I work through it. So just to remind you, we're talking about gases. They all share, regardless of their identity, several physical properties. And the physical properties we're focusing on are pressure, temperature, and volume, at least for these first four gas laws. The number of moles is also an important property. And once we get to the fifth gas law, which is called the ideal gas law next week, we'll actually deal with differing numbers of moles. But a couple things to be careful of. With pressure, make sure both pressure units, if you have a P1 and a P2, in other words, two different pressure values, make sure they're both in the same unit. It doesn't matter which of the three units you use, whether you use kilopascals, which is the SI standard, or atmospheres, or millimeters of mercury, also called torr. But both pressure 1 and pressure 2 have to be in the same unit. And if you're looking for pressure 2, for instance, and pressure 1 is in kilopascals, pressure 2 you'll get out in kilopascals. That will be your units for your answer. So pressure is how hard the particles hit the sides of their container, how hard and how often. So it's how hard they press on whatever surface they're pressing on. Temperature is how fast the particles move. And that has to be in kelvins. I talked about that before, which is just Celsius plus 273. If you get a temperature in Celsius, convert to kelvins before you do any math. Make that the first thing you do. And finally, volume, which is measured in milliliters or liters. It's measured in some form of liters. And that's just how much space the particles are taking up. And so usually we're dealing with contained gas particles for our laws. So contained in either a container that can change shape and size or one that can't. So I'm going to go over the laws really quickly. So here are the four gas laws that you have learned so far, that you should have at least looked at so far. Boyle's law, Charles' law, Gay-Lussac's law. Yes, I know it has a funny name. Combined gas law. And again, later on we will learn three additional laws, but each of these deals with pressure, temperature, and or volume. The first three, Boyle, Charles, and Gay-Lussac's, deal with two of those variables, and the other variable is constant. So for example, Boyle's law deals with pressure and volume. So pressure and volume are changing. Temperature is constant for Boyle's law. Also, the number of particles for all of these is constant. So you aren't adding or removing gas. Charles' law, volume over temperature equals volume over temperature, assumes that pressure is constant. So volume and temperature change, but pressure does not. Gay-Lussac's law, which is pressure over temperature in the first instance, equals pressure and the temperature over temperature in the second instance, deals with pressure and temperature, and volume is constant. And then finally, the combined gas law, which was actually combined by Dmitry Mendeleev. He's the guy who actually looked at all these laws and says, oh, they're actually the same law. I can put them all together. Is P1 V1 over T1, so pressure times volume divided by temperature equals pressure times volume divided by temperature in the second case. Only thing that's constant here, the only thing that's constant is the number of particles. So pressure, volume, and temperature are all changing, but as long as you plug in the appropriate numbers and rearrange the equation, it's really not that bad. The little subscripts 1 and 2 just mean before the change and after the change. So I will go through really quickly. I'm not even going to do the math, just running through some problems, showing you how to set them up, one of each type, and hopefully that'll help you a little bit. And then, of course, like I said, I'll put up a key and work through some of the problems, or maybe all the problems on these two worksheets. But I do want you to kind of get used to figuring these out for yourself. I've given you the problems, given you the equations. You should be able to apply them. After all, you are the honors students. So, first problem, a balloon contains 30 liters of helium gas. As I go through these problems, I like to kind of just label my variable. So 30 liters is volume. I'll just call that volume 1. At 103 kilopascals. Well, I'm going to call that pressure 1. That pressure goes with the volume 30 liters. It's 30 liters while it's 101 or 103 kilopascals. So that's why it's V1 and P1. What is the volume? So V2 is my question mark of the helium when the balloon rises to an altitude where the pressure is only 25 kilopascals. And again, we're assuming that temperature is constant. So it's going to be P1 times V1 equals P2 times V2. We're going to apply Boyle's law to this, and we're going to isolate V2. So we're going to isolate volume 2 by dividing both sides by P2. So the rearranged equation, and again, you guys should be able to rearrange equation, but the rearranged equation we get this is volume 2 equals pressure 1 times volume 1 divided by pressure 2. And we have all these variables. It's just a matter of plugging them in. I plug them in down here, 103 kilopascals divided by 30 liters, or times 30 liters, excuse me, divided by 25 kilopascals, and we get a new volume, a second volume of 124 liters. And you can figure out if that makes sense, because a lot of this is fairly intuitive. If the pressure goes down, that means the gas isn't being pushed upon as hard, or it's not pushing the sides of its container as hard. That means, since the gas particles are at the same temperature, so they have the same kinetic energy, the container must have gotten bigger. Because if they have the same kinetic energy, the only thing that can keep them from hitting the walls with as much pressure is having them hit the walls less often. In other words, put the walls farther apart, it takes longer for the gas to bounce from one wall to another wall. So we would expect if pressure goes down, volume would go up. So moving on to another quick run through. So what is the temperature? So it's asking for T1. I just call the first one I hit T1. Of a 2.3 liter balloon, which I labeled volume 1, that's a volume. If it shrinks to a volume, so I'm given volume 2 of 0.632 liters when it is dipped into liquid nitrogen at a temperature of 77 Kelvin. Notice this temperature is already in Kelvin. I don't have to do anything to it. The temperature is just 77 Kelvin. So volume 1 over temperature 1 equals volume 2 over temperature 2. That's a Charles law equation. And we're rearranging for temperature 2. Now, this is something I would suggest you do. You can rearrange by just cross-multiplying, and I know you guys love to just say cross-multiply, and if you really know what you're doing, it's fine. It's acceptable. But I find that about 50% of the time, a lot of you just mess it up, mess up the cross-multiplication. So since this is a ratio, V1 over T1 equals V2 over T2, you can invert the ratio and it still equals. So since we're looking for something on the bottom, T2, I just inverted the ratio. T2 over V2 equals T1 over V1. Actually, we're looking for T1, I'm sorry. But either way, if you're looking for something on the bottom, invert the ratio instead of trying to rearrange it with the unknown in the denominator. It just makes it easier. So once you have this, it's really easy to see that you just need to multiply both sides by V1 to isolate the first temperature. And I've done that here. T1 equals T2 times V1, excuse me, over V2. And I plug in the numbers. So the second temperature was 77 K. The first volume was 2.3 liters. The second volume was 0.632 liters. And so your first temperature was 280 K. Does that make sense? Well, the balloon 1 was dipped in liquid nitrogen, so it probably got colder. So it makes sense that, you know, the first temperature was bigger. Also, though, if gas particles are going faster, if pressure is being held constant, if gas particles are going faster, that means the sides of the container should be bigger when the gas is going faster, because it's hitting the container with the same amount of times and force. So you'd expect a bigger container to associate with a higher temperature. And in fact, in the first instance, you had a 2.3 liter container. Second instance, you had a 0.632 liter container. So you'd expect that bigger container to associate with a higher temperature. As temperature goes up, you would expect volume to go up. Pressure and volume, by the way, are inverse. As pressure goes up, volume goes down, which makes sense. If you squeeze something to a smaller volume, it gets a higher temperature. If you take a balloon and you try to squeeze it into a smaller volume, the pressure gets harder and harder and pushes back harder on you the smaller you squeeze that container. Okay, two more really quick. A gas in an aerosol can at a pressure of 103 kilopascals and a temperature of 25 degrees Celsius. The can is thrown into a fire. What will the pressure be if the temperature reaches 928 Celsius? So the first thing I did after I labeled T1, P1, T2, and P2 is I just changed the Celsius to Kelvin. Before I did anything else, before I even rearranged the equation, I changed my Celsius numbers into Kelvin numbers because they have to be in kelvins for this to work. So this is a Gay-Lussac's law equation, pressure over temperature in the first instance equals pressure over temperature in the second instance. We're looking for P2, pressure 2. So to rearrange it to isolate P2, we multiply both sides by temperature 2, which I've done here. Pressure 2 equals pressure 1 times temperature 2 over temperature 1. We have all these numbers. We just have to plug them in. Also, you'll note that if you plug in all those numbers, what you're left with for our units, since the kelvins here cancels out, the kelvins and the temperature is kilopascals, which is a pressure. So that's what you would want. You would want kilopascals. We get that, and we see it's 415 kilopascals. You would expect the temperature to go up if it's in a fire. The pressure to go up if it's in a fire. Also the temperature, I suppose. But if you have a can, which isn't going to expand or contract, it's going to stay the same size. So volume is constant. If you heat up the particles, they're going to hit the sides more often, and they're going to hit the sides faster. So harder and more often, that means more pressure. And in fact, the pressure did go up. It went up from 103 to 415 kilopascals. Finally, last one is a combined gas law problem. So nothing is constant except for the number of particles. So the particles are enclosed, but volume, temperature, and pressure are all changing. So the volume of a gas-filled balloon is 30 liters at 315 Kelvin and 153 kilopascals. Note the temperature is already in Kelvin, so I just left it. I labeled V1, T1, and P1. What would the volume be at standard temperature and pressure? So standard temperature and pressure is 0 degrees Celsius, which is 273 kelvins. That'll be T2. And standard pressure in kilopascals, and we want to use kilopascals because we used it here already, is 101.3 kilopascals. So we start with the combined gas law because we're changing everything, volume, temperature, and pressure. None of it's remaining constant. We're looking for volume in the second instance, so volume after the change, but pressure, temperature, and volume are all going to change. So P1 V1 over T1 equals P2 V2 over T2. We want to get volume 2 by itself. In this case, I literally, for some reason, you guys don't mess up the cross multiplication with this one as much. I literally drew the arrows to show you where they should go. So we'd multiply both sides by T2 and divide both sides by P2 to isolate the second volume. And you get P1 times V1 times T2 over T1 times P2. It's a pain to say, but again, 5 variables you all have. We're given all those variables. So you just plug them in and do the math. And you find that in the second instance, the volume is 39.5 liters. With combined gas law, since there's more than one thing changing at once, or more than 2 things changing at once, it's a little hard to intuitively know whether it should get bigger or smaller. So you just kind of have to trust your math on this, but you might want to double check. We're looking for the second volume. So you cross out your units, and you should end up with liters, which we do, which is a good sign. So again, I'll go back to the gas laws really quick. Oops, skipped it. These are the 4 gas laws you should, at this point, know. You should be able to apply them. And just remember, in every situation, you're given all the variables except one. You just have to rearrange the equation, isolate that variable, and plug in everything else. So it's not a bunch of steps. Just rearrange the equation and plug in all the variables you know, and you'll be good to go. Just be careful with temperature. Make sure it is in kelvins, and with pressure, make sure you use the same unit both in the first instance and in the second instance. I hope that helps clear things up a little bit. There is another PowerPoint to go over, and your Gay-Lussac's and combined gas law worksheet is due this Thursday. And again, there's a PowerPoint for Boyle's law and Charles' law that's covered in the gas intro PowerPoint. Gay-Lussac's and combined is covered in gas laws part 2, both of which are available. Okay, have a good day, gentlemen. I shall talk to you again soon.